consider confidence interval estimation. Till now we have concentrated on the point estimation of a given parameter. So, in the point estimation we propose one value for the parameter to be estimated. For example, if we are estimating say average income levels of persons of a particular state. So, we give a value, say we say the value is 2000 rupees per month. So, we are assigning a single value, but the problem with the point estimation is that that value is not necessarily the actual value, because we do not know the true value. A more practical approach could be to give an interval of the values, rather than saying it is 2000 rupees per month, we may say the value is say 1900 rupees per month to 2100 rupees per month. So, now since we are basing our decision on a random sample, therefore, a certain probability is associated with this statement. This is known as confidence level. So, formally speaking, we define a confidence interval as follows. So, we are discussing interval estimation, and as I mentioned that since a probability statement is associated with that, we consider confidence intervals. Okay. So, let x be a random variable with distribution say p theta, theta belonging to script theta. So, let x 1 x 2 x n be a random sample from this distribution. So, let say T 1 x and T 2 x be two statistics such that probability that T 1 x is less than or equal to say g theta less than or equal to T 2 x is equal to 1 minus alpha for all theta. Then if the random sample x is equal to small x is observed, we say that T 1 x to T 2 x is a 100 1 minus alpha percent confidence interval for g theta. So, what is the interpretation of this? That if we take 100 samples and we calculate the value T 1 x and T 2 x, then this interval is likely to include the g theta value 95% of the times. So, this is the meaning of the confidence interval, because the probability of this statement that T 1 x less than or equal to g theta is less than or equal to T 2 x is 1 minus alpha. Therefore, 101 minus alpha percent of the times the interval T 1 x to T 2 x will include the true parameter value g theta. So, now from here we understand that if I take alpha to be a small value, say I take alpha is equal to 0.01, that means 1 minus alpha is 0.99. So, that means we will have 99% confidence interval. So, the smaller alpha value, the larger is the confidence level. Now, how to find out the confidence intervals? What you will call to be a desirable confidence interval? Naturally, if we have higher confidence level, then it is good, because we can say that this is likely to include the true value. However, there is a certain contradiction here, because if we increase the probability, then naturally the size of the interval will also increase. So, there is a conflicting goal, that either we increase the length of the interval, either we increase the length of the coefficient, that is magnitude of the coefficient, or we decrease the length of the interval. So, we have a theory of fixed width confidence intervals or fixed confidence coefficient. That means, we find shortest length confidence interval with fixed confidence coefficient. This theory is closely correlated with the theory of finding out best tests of hypothesis. So, we will not get into that right now. So, what is required here is that for a given parameter, we should be able to find out two statistics such that this probability is independent of the parameter, because this is fixed value 1 minus alpha, it is not dependent upon theta. That means, we should be able to consider certain quantity where g theta is involved, and I am able to write down the distribution of that which is free from the parameters. So, a well known technique here is called the pivoting technique, and we make use of the well known sampling distributions that we have done. So, let us consider confidence intervals for parameters of normal distribution. So, we have the following setup, that I have a random sample x 1, x 2, x n from a normal population with mean mu and variance say sigma square. So, here the parameters are mean and variance, and we are interested in the confidence intervals for mean and variance. So, let us consider say confidence interval for mu, that is the mean. Now, there can be two cases. One case is that sigma square is known. Now, here we make use of the sampling distributions of x bar and s square. So, when we are considering mu, let us consider x bar. We know that the distribution of x bar is normal with mean mu and variance sigma square by n. So, from here we can construct z is equal to x bar minus mu divided by sigma by root n. So, this will have normal 0 1 distribution. Now, you see this is a important statement, because here I have able to create a function of random variables and the parameter for which I need the confidence interval, such that the distribution of this quantity is free from the parameters. So, now if we make use of the normal distributions probability points. So, if this is the PDF of a standard normal distribution, then let us consider the point z alpha by 2 and minus z alpha by 2, that is this probability is alpha by 2, this probability is alpha by 2. Then I can write down the statement probability minus z alpha by 2 less than or equal to z less than or equal to plus z alpha by 2 is equal to 1 minus alpha. that is the probability of this random variable lying between this range is 1 minus alpha. We are showing phi z here, this is z. Let us write down this statement elaborately. So, this statement is equivalent to probability of minus z alpha by 2 less than or equal to root n x bar minus mu by sigma less than or equal to z alpha by 2 is equal to 1 minus alpha. We adjust this term, we multiply by sigma by root n on both the. So, we get minus sigma by root n z alpha by 2 less than or equal to x bar minus mu less than or equal to sigma by root n z alpha by 2, that is equal to 1 minus alpha. Now, this is equivalent to, now if you look at this one, this is equivalent to that mu is greater than or equal to x bar minus sigma by root n z alpha by 2, and if I take this side, then it is equivalent to mu is less than or equal to x bar plus sigma by root n z alpha by 2. So, this statement is equivalent to x bar minus sigma by root n z alpha by 2 less than or equal to mu less than or equal to x bar plus sigma by root n z alpha by 2. This probability is equal to 1 minus alpha. So, if we compare with the definition of the confidence interval, then this quantity is equal to T 1 x, mu is g theta, and x bar plus sigma by root n z alpha by 2 is T 2 x. That means, we are able to obtain two functions of random observables, which include the given parameter with a given probability 1 minus alpha. So, we can say that x bar minus sigma by root n z alpha by 2 to x bar plus sigma by root n z alpha by 2 is a 1 minus alpha percent confidence interval for mu. That means, when I have the sample x 1, x 2, x n, here sigma is known, then easily I can calculate x bar, sigma by root n, and z alpha by 2 will depend upon the value of alpha. Suppose I say alpha is equal to 0.05, that means, I want a 95% confidence interval. So, then z alpha by 2 means z of 0.025. From the tables of normal distribution, one can see that this value is 1.96. So, for example, if say x bar is equal to some value say 2, say sigma is equal to 1, suppose n is equal to say 4 and alpha is equal to say 0.05. Then you have z alpha by 2 is equal to 1.96. So, x bar plus minus sigma by root n z alpha by 2, what this value will be equal to? 2 plus minus 1 by 2, 1.96, that is 2.98 as the upper value and 1.02 as the lower value. Basically, we are getting 2 minus 0.98 to 2 plus 0.98. So, this is the 95% confidence interval for mu. If we had a larger sample size, we can easily see that as the n will increase, the sample size is more, then sigma by root n will become a smaller value and the length of the confidence interval will shrink. That means, accuracy will be more. For example, suppose here n is equal to say 25, then this value will become 2 plus minus 1 by 5, 1.96. So, the value is actually 0.392. So, that is equal to 1.806 to 2.392. So, you can see that the interval is sharper and therefore, you have more confidence in a smaller interval rather than a large interval, and this will give you a more precise information. You can see another thing, suppose I have alpha is equal to 0.1 or suppose I have alpha is equal to 0.01. Then you can see that if I have alpha is equal to 0.1, that means I need only 90% confidence here, that is 1 minus alpha will become 0.9. Naturally, the interval will become smaller. If I have alpha is equal to 0.01, that means it is a 99% confidence interval. So, the interval length will become more. So, depending upon your compromise situation, that how much confidence you need for the parameter, you can appropriately adjust your interval. Now, let us take another case here. Because in general sigma may be unknown. Then naturally, you can see here that this confidence interval cannot be utilized, because this requires a knowledge of sigma. So, here we make use of the sampling distribution of S also. So, we have x bar follows normal mu sigma square by n. Then if we consider n minus 1 s square by sigma square, where s square was defined as 1 by n minus 1 sigma x I minus x bar whole square, that is the sample variance. Then this follows chi square distribution on n minus 1 degrees of freedom. We also know that x bar and s square are independently distributed. This we had done in the theory of sampling distributions. So, if I have a normal variable, I can convert it to a standard normal, that is root n by sigma x bar minus mu. This follows normal 0 1. So, root n x bar minus mu by sigma divided by root n minus 1 s square by sigma square into n minus 1. This follows t distribution on n minus 1 degrees of freedom. So, after adjustment of these coefficients, we can see that this is equivalent to root n x bar minus mu by s. This follows t distribution on n minus 1 degrees of freedom. Once again, you observe this statement. This involves the random observables, the parameter for which I need the confidence interval, that is mu, and the distribution of this function of observation and the parameter is a distribution which is known. That means, it does not depend upon the unknown parameters mu and sigma square. Therefore, once again we can make use of, let me call this quantity as t. Then the distribution of t, as we know, it is symmetric about the origin. So, if we have t alpha by 2 n minus 1 and minus t alpha by 2 n minus 1, this is the density of a t variable on n minus 1 degrees of freedom. Then this probability is alpha by 2, this probability is minus alpha by 2. So, this intermediate probability is 1 minus alpha. So, we can write down the statement probability minus t alpha by 2 n minus 1 less than or equal to t less than or equal to t alpha by 2 n minus 1 is equal to 1 minus alpha. So, from manipulating this statement, we will be able to derive the confidence interval for mu. So, let us see this. This is equivalent to probability of minus t alpha by 2 n minus 1 less than or equal to root n x bar minus mu by s less than or equal to t alpha by 2 n minus 1. So, this probability is equal to 1 minus alpha. So, Once again, if we multiply by s by root n, we get minus s by root n t alpha by 2 n minus 1 less than or equal to x bar minus mu less than or equal to s by root n t alpha by 2 n minus 1, that is equal to 1 minus alpha. So, once again after simplification, this condition is equivalent to mu is greater than or equal to x bar minus s by root n t alpha by 2 n minus 1 and mu is greater than or equal to x bar plus s mu is less than or equal to x bar plus s by root n t alpha by 2 n minus 1. So, x bar minus s by root n t alpha by 2 n minus 1 less than or equal to mu less than or equal to x bar plus s by root n t alpha by 2 n minus 1. So, this probability is equal to 1 minus alpha. So, x bar minus s by root n t alpha by 2 n minus 1 to x bar plus s by root n t alpha by 2 n minus 1. This is a 1 minus alpha % confidence interval for mu. So, how to obtain the confidence interval in a practical situation? We observe the sample, we calculate the mean and the sample variance, and then we look at the confidence level that we want. Suppose alpha is equal to 0.1, then we look at t at 0.05. Now, suppose there are 10 observations, then we look at t 0.059 from the tables of the t distribution and evaluate this value. So, that will be a 90% confidence interval for the parameter mu. Let me give one example here. So, 10 bearings made from a certain process have a mean diameter 0.0506 centimeter and a standard deviation 0.004 centimeter. That means, the sample has been collected on 10 bearings and its mean, that is x bar, has been calculated and the standard deviation, that means s, has been calculated and n is 10 here. Assuming that the data may be looked upon as a random sample from a normal population, construct a 95% confidence interval for the actual average diameter of bearings made by this process. So, if we are considering x 1, x 2, x 10 as the 10 observations on these bearings. So, that means, these are denoting the diameters, then this is following normal mu sigma square. So, this actual average diameter is mu here. Now, we do not know the values of mu and sigma square. So, from the sample x bar has been calculated and s has been calculated here, n is equal to 10 here. So, if we want a 95% confidence interval, that means, we need the value of t 0.025 n minus 1, that is 9. So, this value from the tables of t distribution can be found, and that is 2.262. So, we calculate here x bar plus minus s by root n t 0.0259, that is this value is 0.0506 plus minus 0.004 divided by root 10 into 2.262, which is equivalent to 0.0506 plus minus 0.0028612. So, if we evaluate the lower and upper limits, it is 0.0477 and 0.0535. So, this is a 95% confidence interval for mu.